Now it's a great pleasure to introduce tonight's speaker, Dr. Timothy Rodigas from the Carnegie Institution here in Washington at the Department of Terrestrial Magnetism. He got his bachelor's degree at the University of Virginia and his PhD in astronomy at the University of Arizona for a thesis in which he studied planetary systems and their circumstellar environments using high contrast imaging at near-infrared wavelengths. He then became a Carnegie postdoctoral fellowship at the DTM, and this year he was awarded the 2015 wow, Hubble Fellowship.
Yelling his age.
Generally regarded as the most prestigious fellowship in astronomy. That's really, congratulations. Most of Dr. Rodigas' work uses high contrast imaging of exoplanets and debris disks to discover what the debris disks can tell us about the masses, orbits, and compositions of the planets. In particular, he figures out what the shapes and structures of the debris disk can tell us about planets, and what the chemical compositions of the dust grains can tell us about the presence or absence of water and organics, which are thought to be essential for the development of life. For example, he's used measurements of the structure of debris disks to find planets that are actually gravitationally shepherding material in the debris disks, much as some of the moons of Saturn shepherd some of Saturn's rings, holding them in place and protecting them against disruption. In addition to imaging at visible wavelengths, he has extensively imaged at near and mid-infrared wavelengths, and in particular has used observations at those wavelengths to study brown dwarfs, planets so massive that they almost could have become stars. He's also searched for cometary grains in debris disks, which is quite remarkable, and has also imaged and characterized a dust-enshrouded exoplanet orbiting Omicron. Another aspect of his work has been the use of state-of-the-art optical technology, use of adaptive optics to study the atmospheres of exoplanets, the use of the large binocular telescope interferometer and adaptive optics system, the Space Telescope imaging spectrograph on the Hubble Space Telescope, and soon he's going to be going down to work on the Magellan Telescope. Dr. Rodigas.
Thanks. It's great to be here. Thank you for inviting me, and I really enjoyed the dinner and chatting with you. And yeah, perfect. Perfect.
The backlight.
Yeah, that's better.
Much.
Should I, Father, should I stand over here or over there?
Right where you are.
Here?
Yeah.
Okay.
Right. Yeah.
Okay. And thanks for the introduction. That's I didn't realize. I mean, the list of things sounds strange. Hearing you list all those things, I didn't realize. I forgot that I've done some of those things. So I guess I've been in astronomy for a while now. So yeah, today I'm going to tell you about my work on imaging planets and disks around other stars, exoplanets and extrasolar debris disks. And in particular, the running theme is basically the key. The reason I'm able to do this is the high resolution capabilities of the instruments that we use. Before I start, I should just acknowledge all the collaborators that I've worked with. Some of you have already seen talks by them, actually, which is really interesting and really nice. And in particular, Alicia is my advisor at Carnegie, and these are some other postdocs and scientists at other nearby institutions.
We know most of them.
Yeah, they're all very, 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 very smart. And without them, I'd be lost. So let's start with the concept of resolution. Because before I get into any analysis of data, it's important that we're all on the same page in terms of what resolution means for astronomy and how that relates to finding planets and disks around other stars. So resolution in astronomy basically can be described by this diagram. You have two stars, binary, and they're emitting light, and that comes to our telescope. If you can see both those two stars with your telescope, then that's considered resolved. And by the way, let me just interrupt myself. If you have questions, please just ask me throughout. You don't need to save them until the end. Okay, so that's a resolved system, when you can see both stars with your telescope. If you just see one star, and there's actually two there, it just looks like one little blob, that's considered unresolved. So resolution is defined by this simple equation, lambda, which is the wavelength of the observation, over d, the diameter of your telescope. So here's lambda, and there's d. And our eyes are basically telescopes, and so if you wanted to, I won't ask you to, but for homework you could work out what the human eye resolution is, and I'll be curious to see. I mean, it's pretty straightforward. You know the size of the eye, you know the wavelength that we look at, which is roughly visible 0.5, 0.6 microns, and so you just divide those two and you can get an answer. It's really cool. So that's what resolution is, and that is theoretically. So theoretically, if you want high resolution, you basically just you tweak this ratio right here. You either increase d or make lambda smaller. So make a bigger telescope or shorten your wavelength. However, that's not how it works on Earth. So making a bigger telescope actually does not give you better resolution because of the atmosphere. And so you're all familiar with the children's rhyme, "Twinkle, Twinkle, Little Star." Twinkling is bad. We don't like that in astronomy. It's very bad. It's a nice children's song, but when you see a twinkling star in the night sky, you should remind yourself that twinkling is stopping you from seeing the planets and disks that are around that star. And so we want to basically remove that twinkle so that we can see the things we're interested in. So to just show you this with a cartoon, your average nearby star it basically has planets. This is something that we've learned from Kepler, the telescope that's in space, that's staring at 150,000 stars over and over, getting transits, seeing as planets block the starlight. And so the statistics from Kepler is showing us that almost every star has a planet, and potentially multiple planets. So in that respect, our solar system is not unique. There are plenty of planetary systems out there, just like our own, potentially. So this is what your average star would look like. But when you actually look at it, this is what it looks like. It's a big blob. In fact, this is a movie that came out when I was young. I mean, it basically just ruins everything. It crashes the party and destroys your ability to see, the planets and disks, around these stars. So we want to get rid of the blob, of this annoying point spread function halo. That's basically what it is, and it's caused by the atmosphere. So just to give you guys a little more idea of what seeing does to you. So if you have a star and a planet, you have the light coming from both. The star is emitting light and the planet is emitting light. Planets, especially ones like Jupiter and actually even Earth, when they form, they're hot when they first form. And they continuously cool throughout as they get older over time. And so actually, the reason we can even see any planets, I'll show some pictures later, is because we're looking in the infrared. We're basically using heat vision to see their glow from formation. And so both the planet and the star are emitting light. But that light comes into Earth's atmosphere, these little pockets of turbulence, and it basically just becomes this big blob. And as I said earlier, you can use a big telescope or a small telescope, doesn't matter. Your resolution is going to be the same. You don't get any gain in resolution by going to a bigger telescope, although you will collect more light, so you can get a higher signal noise measurement. But in terms of resolution, you cannot distinguish between those two close stars. They're going to look like just one big blob. Here's a nice little schematic showing what actually seeing does. So you have your starlight come through, and basically it's packed. It's all skewed up and messed up as it comes to your telescope because of the atmosphere, because of the turbulence in the atmosphere. And so you can see basically your imaging, when you image the star, when you actually record the image, it's basically the superposition of a bunch of images of the star itself bouncing around all over the place. And so that's why it looks like a big blob instead of, you know, a nice sharp image. And this is a little dark, but this is actually the moon, observed with a telescope from Earth. And you can actually see the features on the moon are just wobbling all over the place, and that's because of seeing. So you should all be on the same page with me now that seeing is bad, the atmosphere is bad, twinkling is bad. We want to get rid of that. So there's three real ways that we can do this. The first is we can go to space. That's really, really expensive, but we've done it. And HST, Hubble, as you guys were mentioning, has done great science. It's been up there for 20-some years. 25 years, that. So, I mean, it's absolutely a spectacular instrument. It just costs a lot of money. So there are cheaper ways of beating seeing. There's a second method, which is called lucky imaging. And I won't get into too much details, but basically it involves taking very short exposure images so that you freeze the pattern of the star bouncing around. You freeze it basically, and you select only the images that are particularly high resolution, because the atmosphere is changing, and so sometimes you actually do get good. You just by chance get a really clear path for the light. Other times you don't. So if you take a lot of really short exposure images, you can filter out the ones you don't like and keep the ones you do. This is if you use everything, just a whole bunch of stars imaged. This is if you filter out the ones you don't like, and you can see this is obviously sharper than this other one here. So that's one way, but that only works up to a certain point. It can't really get you down to the diffraction limit, which is the theoretical best resolution you can get for a certain wavelength for a certain sized telescope, a certain diameter. The third way is adaptive optics, which is basically the compilation of these two things. It's cheap because it's from the ground, it's cheaper, but it involves a lot of time, a lot of struggles. I've heard stories of when they were first, so the University of Arizona was a real pioneer in terms of more advanced adaptive optics. There's adaptive optics at the Keck telescopes. They've been doing that for years, but Arizona started basically adaptive optics that uses the secondary mirror of the telescope rather than the tertiary or fourth, fifth, sixth, seventh mirrored, because that can theoretically give you better performance and allow you to image planets, because planets, as I said, are bright in the infrared, and every mirror in a telescope glows, and so that adds noise. So if you reduce the number of mirrors in your light path, you can see fainter things. So adaptive optics is a real key for exoplanet imaging, and Arizona was a leader in that. And at the MMT, the multiple mirror telescope, which is actually, it's a misnomer. It used to be multiple mirror, now it's just a single primary mirror, but it's still called the MMT. They actually still have the first adaptive secondary iteration. And I've heard stories of people crying at the telescope because they could not get it to work, the adaptive secondary. And so it really takes a lot of effort, but once we've learned a lot of lessons along the way, and so now we've put adaptive optics at the LBT, at Magellan, which I'll show images from. And so we've really gotten much better at it, and fewer tiers now, actually. Okay, so here's a little schematic showing how adaptive optics works. Here's your star and planet. It's in space. The light comes out like a normal perfect wave, and it gets all distorted because of atmospheric turbulence. And what adaptive optics does is it has a mirror here, which is going to be pushed by pistons behind it 1,000 times a second, all over behind the mirror, just by little small amounts, to perfectly correct for what the atmosphere does to that starlight. Because we know what the starlight should look like. It should look like a perfect point spread function, which we know we can theoretically work that out just from optics. We measure how it does look. It looks all distorted, and then we correct for that in real time. Now we're always trying to catch up because you record the image, you see what the atmosphere was doing, you tell the mirror to move to correct for that, and then the mirror. But then when it corrects for it, the atmosphere has changed. So you're always playing catch up, but you can still do quite well. what the schematic shows is how this works. Basically, I have something called a wavefront sensor, which is what measures this distortion. It basically then tells the mirror to bend in a certain way to correct for that. And eventually, if you've done things right, you should be able to recover the perfect diffraction-limited image that you would have seen if you were in space. So just to give you an idea, wow, that really, oh, anyway, it doesn't show up as nicely as it does here, even though it is a big blob. This is a star image without adaptive optics, and when you turn on the AO, you see 2 stars. So you should think, anytime, I mean, I love all astronomy, I love the research that people do, but doing astronomy without adaptive optics is kind of like being blind. I mean, you're just not seeing what's going on. This can actually, this is really, you would have no idea that there's 2 stars there, unless maybe you took a spectrum or did some other, indirect analysis. So just to show you some examples of what AO really does for you, here's an image of the adaptive secondary mirror. This is actually the one that's at the MMT, the one everyone's crying about. Right here, so you can see this is the actual surface of the mirror. It's decently small. This doesn't show up that well, but it's basically a glass pyramid. It's called a pyramid wavefront sensor. There's only like 5 in the entire world. Apparently 1 guy makes them, and Arizona has like 4 of them. So everyone, that's why really Arizona is the only one that can do this adaptive secondary adaptive optics. And so when you use these 2 things together, you can make images like this. These are diffraction limited. This is the LBT, the Large Binocular Telescope in Arizona. It's probably the world's best telescope at one of the world's worst sites. It's actually, I get why they chose Arizona. It's convenient, 3-hour drive. You can fix the instruments really easily. But I mean, the conditions are just horrible. It snows and you're snowed out for weeks. It's really not a great site, but when it is open, it's spectacular.
What mountain is it on?
Mount Graham.
Mount Graham.
Yeah, Mount Graham.
And Mount Graham's a beautiful place when it's nice.
Sure, it's beautiful, but I mean, it's just, I've been there. So we've had runs that were 15 nights long, and we opened for 1 night. Oh. Which is, usually in astronomy, you roughly plan on 60% good weather to 40% bad weather. The LBT, it's probably flipped, 40 to 60 if you're lucky.
Is it clouds or turbulence? Or
it's okay. So clouds are not even the worst. What really killed us? Okay, what really kills us is the snow, because the LBT is such a huge building that they can't have a dome on the top, because if snow falls, then the snow will slide off the top 400 feet, and if you're standing around outside, you could die from snow hitting you. So they have to. So instead, I get why they did this. They basically decided to collect the snow on the roof, melt it, turn it into water, and then eventually you can open. The problem is it gets so cold that the heaters freeze, and so then when it snows, you're basically stuck for 4 nights. So it'll snow, and then it'll be clear for 3 nights, and you can't open. Wow. Which is really frustrating. Another big killer is humidity. It can be very wet there. So it can be perfectly clear, no wind. And if it's 98% humidity, you can't open, because the instruments will water plus adaptive optics is very bad. They've had water problems at the MMT and the LBT for being too humid. And then the third killer is wind. That's just, you're not going to beat that anywhere. I mean, that's a problem with all ground-based telescopes, is if it's too windy, you got to close.
That's the highest mountain in Arizona. You'd think it would be protected by the Vatican Observatory.
Yeah. Unfortunately, they don't use their powers to...
Isn't this a desert location?
At Arizona?
Yeah.
On top of the mountain, it's basically trees and forest and squirrels. You need a squirrel permit.
Yes.
I had a squirrel permit.
Red squirrels.
Yeah, to go up there. So it is a desert climate. There are other mountains in Arizona that are, Arizona is basically a desert, at least near Tucson. And even still, you still get clouds, you still get all these other problems, moisture. Really, where you want to be is Chile, and I'll explain that soon.
what's a squirrel permit?
The squirrel permit is you need to sign something saying that you're not going to you're not going to mess with the endangered red squirrel population that's indigenous to the LBT's area.
You don't eat squirrel, right?
Yeah, so I try to, yes, question.
Why is humidity so bad
For
adaptive optics versus all the reasons why humidity is bad, period?
well, I mean, so we have some computer people here. You generally don't want to spill water on your computer.
Okay.
Right? So it's the same sort of deal. Yeah. Any other questions?
There's all these sensors.
And it absorbs the infrared.
It's also.
Okay,
I'll explain why. As John mentioned, I'm interested in finding water and organics around other stars. It's very hard to actually see those features because of the atmosphere and because of the water in the atmosphere, but it can be done.
The best I can make out of that wavefront sensor seems to have annular segments.
Yeah, so it's actually there's like a it's like a four-sided pyramid kind of shape. I almost want to turn my computer so you can see. I don't know if you can see that.
Well, you can see it better.
Oh yeah, it's beautiful this way.
So
Get up close, Walter.
I don't know if you can make the projector brighter.
He can at least
Okay,
get it.
I'll just leave this facing you guys so you can see anything.
Okay. Thank you.
Yes. Okay. So that's basically. So let me just clarify. These images are diffraction limited and are absolutely beautiful. These rings are called area rings. They're from. You expect them. It's an airy pattern. And to see so many, you actually can't see it there, but you can see it here. There are 14 area rings, and it's quite beautiful. You can't do this at other telescopes. Any other questions about this?
Is that like the swaths that, like around Saturn, you've got rings?
This or no this?
The rings.
No, the rings is just that's what you get. It's an airy pattern. It's from diffraction. Exactly. It's exactly what you expect. That's what a star should look like instead of that big blob I showed.
Yeah.
Okay, so here's this is Chile. Basically, this is the Magellan telescope. So there's actually two telescopes. I only go to this one, and the adaptive optics is part of Magellan, and so we call it MAG-AO. And it happens at this one, so I don't care at all what's going on here, except sometimes we take their food if we're hungry. And we have two cameras, two instruments that are synced up with MAG-AO. One is the visible camera called VisAO, and so that offers diffraction-limited adaptive optics at visible wavelengths. And I know we all love Hubble, but this can get, basically, it can do what Hubble can do from the ground and at higher resolution.
Wow.
Hubble can go deeper because you don't have to worry about the atmosphere. It can see things very faint, but in terms of resolution, we are crushing Hubble. JWST is going to be launched soon, and that's going to have great resolution too, but that'll be in the infrared.
Need to make T-shirts.
Yeah. Okay, so then the other instrument is called Clio, or Clio 2, because we've had two detectors in it. That offers diffraction-limited imaging at 1 to 5 microns in the infrared, and also some low-res spectroscopy. Clio actually used to be at the MMT, and once we were sure that MAG-AO was going to happen, we decided to move Clio to Magellan, because the southern hemisphere for exoplanets and disks is where you want to be looking. There's really not much going on in the northern hemisphere. There are a couple interesting targets, but there's a lot more stuff going on in the southern hemisphere.
Is that because you're looking into the Milky Way down there?
And no, it's just because that's where the good stars are. The ones that have disks, have planets. They just happen to be. I mean, there might be some correlation in terms of galactic position, but I think it's just, as far as I know, it's just chance. Okay, here's a nice little movie, and again, if you need to look at the computer, you can to see it better. But basically, this is the adaptive secondary mirror, and what I'm going to show you is basically how the mirror is, all these little pixels, all these little colors are showing you which parts of the mirror are moving. And because the mirror is correcting for what the atmosphere does, you're basically going to see the atmosphere. You're going to see the atmospheric turbulence. So you can see these patches blowing across the atmosphere. And this is not even in the real time. It's actually doing 1,000 times a second. This has been slowed down because the computer can't process it graphically. But you can see the turbulence just going across, and it's correcting.
Is that optimizing on a laser beam? Or
No. This is not laser guide adaptive optics. This is it's called natural guide star. So we're using
Natural guide star, okay.
we're using the star itself to correct, which is actually, I mean, laser guide star is great, but with natural guide star, for exoplanets, you're typically looking close to the star, and so you can just focus in on the star itself,
Oh, yeah, okay.
and you can look at faint stars, bright stars. It's really powerful. Any other questions about this?
How important is the seeing? If you're
The
looking at-
seeing. So in my experience, the seeing. Okay, so are you guys familiar with like 1 arcsecond seeing is okay?
Yeah.
Seeing 1.5 is bad. 2. Okay. So in my experience, what really kills you is variable seeing, at least in terms of adaptive optics. Obviously, you want good seeing, and you don't want bad seeing, because the adaptive optics has to work harder. But what really is, it can happen. I've been there at Magellan, which is a great site, and the seeing will be nice steadily going along at half an arcsecond, which is typical there, and then it'll just spike to an arcsecond 1.5, 1.75 for like 10 minutes. And the mirror basically freaks out. It basically can't handle such a rapid change. And the way the mirror has been designed is safety first, basically. And so when the mirror feels threatened at all, because if the mirror breaks, we're basically screwed. And actually, so if the mirror feels any danger, it rips, and that stands for rest in peace. Basically, it just falls back on and stops moving. Because actually it's magnetically levitated, so it just falls back and stays, and says, and then all the monitors turn red and say, oh my God, something happened. And the story about the mirror being we don't want it to break, it's actually already cracked. And does anyone know the story with this?
No.
Okay, so the mirror, the adaptive secondary mirror, was the LVT is 2 primary mirrors with 2 adaptive secondary mirrors. They had one going, everything. They built the second one, and the second adaptive secondary mirror cracked, and so they were like, we can't use this. And the Magellan people were like, we can use that actually. So they basically sealed the crack and are only using the part of the mirror interior to that, and so that mirror is cracked and doing just fine. So we're using a cracked mirror to image exoplanets, which is really cool. To fix the mirror?
Yeah.
I have no idea. Things in astronomy always cost a lot, so I'm guessing a couple thousand at least, maybe more.
What's the figure of that mirror? Is that mirror a hyperbolic mirror?
Actually, I don't. I think it is, but I don't know for sure, so I don't want to tell you the wrong answer. But
Okay.
It's designed to work with the shape of the primary mirror of Magellan. So yeah.
These
There's some
little red
spots
circles, an actuator, is that right?
There's some spots. What?
There's some spots in the dark side which never turn dark. Are those like hot pixels?
So there are some pixels that aren't moving, and those are they're called, I think the term is slaved actuators, and they're actuators that basically we've tested and they don't really work that well, so we just turn them off. So they don't push the mirror; they just sit there.
So what are we seeing? Is this like an image of the mirror?
This is telling us which parts of the mirror are moving right now, and so that's basically an analog for what the atmosphere is doing, because you can see.
I know that.
Right. Okay. So did I answer your question? Or
So these little spots, they're the different actuators and what their positions are.
yeah.
And
And how
red
much?
would be? What is red? Is that nearest to you? That's pushed up and.
That I don't know. I think it's actually more current, but I don't know for sure. So I don't know for sure.
Okay.
All right.
I'd just like to say, if you take your amateur telescope and just rack the eyepiece out back, like a 1/4 inch, 1/2 inch, something like that, so that you're focusing on the end of your telescope tube, and you have your telescope pointed at a bright star, the star will be out of focus, and you will be seeing images like this through the eyepiece, and what you're seeing is basically the light, the atmosphere, how it affects the variability of the light across your aperture.
Oh, interesting.
If you've never done that, it's very instructive.
Interesting. Okay. All right. I'm just going to move on here. Okay. So with adaptive optics, we can now literally take pictures of planets around other stars
That's so
and
cool.
disks. And so I'm going to show 2 examples here. Does anyone know
Oh, yes.
Well, you can see the
Beta
name,
Pictoris,
Beta Pic.
yeah.
But does anyone know the story behind this right here? No? Okay, so in 2003, Anne-Marie Lagrange in France imaged this star. She saw, well, actually, in the data, there was this object right here, just sitting there. That was in 2003. They didn't look at the data until 2009. And when she did, she said, "Oh, this is a planet. This is amazing." And so the first thing that you want to do when you see an object like this is confirm it. Go to the telescope again, and try to see that it's there again. She went back to the telescope, and there was nothing there. Then, a year or two later, they went back to the telescope one more time, and they saw something on the other side of the star. What happened? Exactly. The planet moved. The planet's orbiting. So I think this is one of the best images ever in astronomy because this shows not only are we seeing orbital motion, we've detected an extrasolar planet around another star. This is a debris disk viewed edge on, and actually you can see there's like this sort of warping of the disk. That's caused by the planet, this behemoth, which is now, we think it's around 11 times the mass of Jupiter.
Wow.
And for those of you that don't know, brown dwarfs they turn on around, they start, fusing, I think, deuterium, I think, or something like that, around 13 Jupiter masses. And so this is just shy of the brown dwarf mass limit. But this is a spectacular system. And question?
Yeah, and how far is that from Earth?
So I think Beta Pic is at like 19 parsecs, which is
Close.
60 light years. I could be wrong. I think it's within 20 parsecs, something like that.
Where does the luminosity arise that lights all that up?
That's the planet's heat. So that's the
planet's heat.
Yeah, that's the planet. That is not reflected light. Right? It's infrared. This star is, actually now it's getting older. So stellar ages is a really difficult thing in astronomy. It's very hard to figure out how old stars are. This was thought to be around 10 million years old, and so we thought this thing was around 8 Jupiter masses because for a certain brightness, if it's younger, then it's less massive. If it's older, then it must be more massive, just to have the same brightness. And now we think that the star is around 25 million years old, and so that pushed the mass up to around 11 Jupiter masses. And actually, people are looking to see, because this thing is getting closer to the star again. It's past its furthest point. It's coming closer. There's a chance it's going to transit its host star.
Wow!
So in like 2019 or something like that.
That'd be nice.
And so we're starting to prepare for that chance.
Why wasn't it a binary? Did it not evolve to the point of having that connection and the mass that it would?
So why didn't this little guy become a star, basically?
Right.
We don't know. We're still learning a lot about how planets form and how they, why some are big, why some are small. So this one, for whatever reason, didn't gobble up enough material to reach that point. Here's another one. This is probably
picture,
what?
Is that with the occulting disc?
This was, I think they used adaptive optics. I think they did use a chronograph. That's what typically they use.
Well, there's something in the middle there.
All the images I show, if there's a hole in the center, there's either a chronograph or that's just the person who made the image digitally in post-processing just making the center 0 so that it's easier to see the planets and disks around the star.
And what wavelength is that Beta Pic picture?
This is I don't know, it's either H or K band, which is 1.65 or 2.15 microns. Okay. So this other image here is of HR 8799. Have you guys heard of that one?
No.
Oh, okay. This one is I think eventually even cooler. So this is 4 planets imaged around another star. This star is, I think, 40 parsecs away. The closest planet here is at 14 AU. This is at 80 AU. And you know how big these things are? 7 to 10 times the mass of Jupiter. How did a 7 Jupiter mass object form at 80 AU? The furthest planet we have in our solar system is Neptune, around 30 AU.
Planets migrate.
Well, okay, so there you go. There's your answer. Well, the truth is we don't know. We're working on it. But migration is one possibility. It could be that disks and gas last longer than we think they do, but people are working on it, and it's very exciting because it's strange. So this is what you can do now with adaptive optics. Both these images are made from the ground. This is how we image planets. Any other questions about this? Okay. All right. So even though you can do this now, these planets are rare. So these planets were discovered, in 2009, 2010. Everyone said, "Oh my God, there must be tons of these." Hundreds of stars were surveyed, were imaged, same way these were. Nothing, or a couple. There's a handful of directly imaged planets now. So the takeaway is that these things are actually rare, or at least if they are out there, they're much closer to their host stars, so we can't see them yet, at least. But it is actually easier to see the disks, this stuff, than it is to see these guys. And just like we have this projector here, and if you look closely, you can see little dust reflections off the dust. There's not even that much dust there. The same thing is happening around other stars. There's dust around other stars that arises from collisions between asteroids and comets, and light from the star bounces off the dust, and we can see that light pretty easily. So just to get us all on the same page when it comes to disks and dust, a debris disk is basically an exo-Kuiper belt, and again, the Kuiper belt is basically the solar system's debris disk outside of Neptune's orbit. And so a typical planetary system, we think, looks like this. It has a star. It has one or more planets. You have those planets clearing out material, and so you see a gap. You actually have, nothing. So you have planets, star, planets, nothing, and then you have your disk, which consists of boulders and dust. And as I said, basically these planets are like Jupiter. Maybe there's Earths, but we're not at the point where we can image other Earths yet. So these guys, even though they're hard to image. Even though I just showed you two spectacular images, those are rare. It's actually much easier to see these funny-looking dust grains around other stars. So here's some actual science now. This is getting into the stuff that I've done with the LBT and Magellan. So HD 15115, you don't need to remember the number, I'm not going to test you on that, but it's basically a sun-like star 45 parsecs away. Here's a not great looking image, but on the computer it probably looks better.
Beautiful.
So this is from Paula Callis, who's at Berkeley. It's an image of basically an edge-on, needle-like debris disk. It looked like a needle, and so it turns out that the colors, when you image at multiple wavelengths, it looked blue. And so he affectionately called it the blue needle. And so this is a pretty famous disk, and if you image now with HST, this first image was from the ground. This next one is with HST at infrared wavelength. You can see already that the asymmetry is changing as you go to different wavelengths. And here's my own image from the LBT at K-band at 2 microns. No one had really been able to get a good image at such an infrared wavelength, such a long wavelength, because the adaptive optics at other places is not up to the standards that the LBT has. And so, like I said, the adaptive optics of the LBT really enables you to image at long wavelengths. So there's a nice image, and it shows the symmetry. Here's an image actually at 4 microns, which is really tough. And I actually had to bin this image by a factor of 4 just to pull out the light right here. You can see the screen.
Are the adaptive changes monitored in the visible appropriate to correct for the like 2 microns?
So we correct for everything at around 1 micron. That's where all the correction, that's where all the sensing is done. And yes, that works up to 4 or 5, even actually 10 microns, and all the way down to the visible as well. Okay, so just zooming in on these pictures, again, they look better on the computer if you want to glance at that. Basically, this shows no longer is it really a needle. It looks just more symmetric at these longer wavelengths. And so what I did was, this is when I was a graduate student, even though it looks less like a needle and more symmetric, you can still see that there's something going on this side of the star. It's nice and smooth on this side, and then there's just really like something's going on. There's some distortion. Something's happening. You can also see that if you trace the brightness of the disk close to the star, it looks bow-shaped. It would cross up here rather than at the center of the star. And so I can make a simple model, like a toy model, and it looks like that. It's basically a ring-like disk viewed edge-on. And so if you put it all together, one explanation for this distortion is that the star is moving exactly along the position angle of the disk, and perhaps it's interacting with the ISM. It's interacting with some bubble where basically the dust in the disk is being affected by the ISM on this side. But on this side, since it's away from the ISM, it's not really affected. So this little cartoon is a representation of what might be going on, although it would help to have some more in-depth modeling. What was really nice is this year, or last year technically, that again doesn't look that great up there, but on here it looks nice. You have basically, this is an image of the same disk with another telescope, and actually what they're seeing is the ring. You can actually see a little gap in there on both sides, and here's a good model representation of that. And so basically the needle is actually a ring. It's like the toy model that I came up with has basically been confirmed, which is really interesting. As I said before, a ring, it means that there's no material, past a certain point. And one possible explanation is planets. Planets means Earths, and Earths means potentially life. So anytime we see a gap, we get excited. Of course, it's very hard to find planets inside those gaps, but we still get excited. So I want you to keep in the back of your minds this slide, because I'm going to come back to it later in the talk. But basically, there are several ring-like disks, but we don't really see the planets. So where are the planets, if they are there, and what could they be like? What are their potential masses? We don't see them. Can we use the morphology of the disk? How the disk looks, how wide it is, any other features, the asymmetry, the eccentricity of the ring. Can we use those features to tell us about any planets that are clearing out material inside of the ring? And so I'll address that later on, but I want you to keep this in the back of your mind. So here's another disk that I've imaged, HD 32297. This is a young, massive, hot star. It's an A star. It's not really like a sun-like star. It's much hotter, more massive. Had 112 parsecs away. So this is, pretty. It's at the edge of the solar neighborhood. 200 parsecs is really pushing it. This is around 100. And this image is from space with HST. Here's a couple more images from HST at infrared wavelengths. And you can clearly see this is an edge-on disk. And the morphology is well constrained. What we'd really like to know is, with all these wavelengths imaged, what is the dust made of? Because as John alluded to in the introduction, if the dust is made of things like water and organics, then that tells us about the reservoir for the ingredients for life. If there's a lot of water and organics, that maybe there's a good chance that that material, via comets and other infalling asteroids, can be, transplanted onto interior Earths. And so if you get that material to the planets, then you have the chance for life. If there's not much of that material, and the solar system is kind of unique in that respect, then that tells us something about how likely life is around other stars. Okay, so now when you want to figure out what dust is made of around another star, the typical method is actually you don't image the disk at all. What you do is you look at its SED, its spectral energy distribution, and for that you basically take an image of the disk at very long wavelengths. This is the far infrared, and you're not even seeing the disk. You're just using Spitzer or some other telescope to just take a picture of the star, and the star should look like a black body. It should just, if there's nothing else there, if it's just the star, it should be a nice black body. That's this line down here. And so if you measure the brightness of the star, and it doesn't follow this black body, but instead rises up at infrared wavelengths, then there must be something that's glowing, or some infrared source by the star. And so that's how. So what people usually do is they just take measurements at far infrared wavelengths, and then they fit models to those to that data. So that's what people normally do. And you make some assumptions about what the sizes of the dust grains are going to be, because there's tons of different sizes of dust grains, and you have to usually just assume some distribution. And what people do is also they make these complex mixtures of a few different compositions. So, they'll take water, organics, silicates, iron, throw them all together into some complex dust grain using models that are really not well calibrated and try to match this data. And so that's how you get quotes like this. Oh, we found an icy Kuiper belt around another star. But as I'll show, this is really not what we should be doing. So for HD 3297, that's this big A star around, the big A star 112 parsecs away. Actually, a colleague of mine at DTM right now, she's a postdoc. She basically used some new infrared data with Herschel to really fill out this curve. Before there was just data out here, they were missing this stuff. And so she got all this data here, and she fit a bunch of models to that, and found that the best match was porous silicates plus carbon plus water ice, which equals basically comets. It's very exciting, and it's really intriguing. The only problem is, like I said, the models are not that great, and really there's other ways to probe the chemical composition of the disk, and that don't rely on just this data here. So, as a sidestep showing what I'm talking about, if you think about the solar system, this is Phoebe, one of Saturn's icy moons, and if you take basically a spectrum of Phoebe using Cassini, you see these features, and this is 1 to 5 microns. What you basically see is that the best match to the data is tholins, which is basically like organic goo. It's been used to describe what's going on Titan, actually. You see water ice, you see carbon. These are all things that are key to life. And these ingredients have features. You see these features right here at 1.5 or 1.6, 2.0, 2.15, and 3 microns. These strong features in the infrared. And it turns out that we have filters that we can image from the ground at these exact wavelengths where these features are. The only problem is, like I said, no one really can image beyond 2, 3 microns. It's too hard unless you have the spectacular adaptive optics system at the LBT in Magellan. Then you can actually image at these wavelengths, but it's still tough. Okay, so what we did is, or what I did as a graduate student at Arizona, is I obtained a new image of this disk at 4 microns. So here's this image of this nice edge-on disk, and so we can now fill in an important part of the spectrum. We're not taking spectra; we're just taking images at different wavelengths, and this is basically a low-resolution spectrum of the dust, of the scattered light. And so we basically tested the comet model that was preferred by Jessica, and found that it was an okay fit. This is actually, best case scenario. It really wasn't that great a fit at all. We basically relaxed all constraints to try to make a good fit, and it was okay. Well, interestingly, we found that just pure water ice, just 100% water ice, was the best match to this data. Unfortunately, what you really need is an image at 3.1 microns, because that's where you have this theoretical feature that's attributed to water ice. And actually, I have an image of the disk at this wavelength. It's in my queue of things to do. So we'll see. Once we've analyzed that data, we can actually see, is 100% water ice the best? Is Comet's good but needs to be revised? Is it something else? We'll really be able to tell what's going on. Any questions about this? Okay. So now let's move on to probably my favorite debris disk. This is HR 4796. Have you guys ever heard of this one? No. Okay, so it's a nice ring-like disk. And remember, we see a ring, we think, what do we think? Planets. Exactly. So it's very exciting. This is an image from Hubble, actually a multi-wavelength color image that John Deves made. And so using this data, he basically, again, made a low-resolution spectrum of the scattered light from visible wavelength to around 2 microns. And what he found was that a good match, not necessarily the best match, but a good match was this outer solar system body, which is thought to be covered in organic material. And so this is a very exciting result. is this dust just rich in organic material? That'd be really cool. So the only problem is, you publish something exciting, you're going to get someone writing a paper saying, no, that's wrong. There's another explanation. And that's exactly what happened. Another group said, well, yeah, we can also fit the data with more simple organics, and that's just, carbon, not necessarily complex organics like tholins and things like that. So, it really wasn't clear what was going on here. Was it complex or simple? And the problem is basically these data are limited to 2 microns. And as I showed with Phoebe, with Saturn's moon, if we image at 3 to 5 microns, we can really potentially pick out features that can distinguish between these two. And so that's exactly what we did. And these don't show up that well at all, but at least these don't. But you can see we've obtained 7 images of this disk at 7 new wavelengths. And I should point out that these 2 instruments work at the same time. So we collect light from the star, and the infrared gets split off and sent to one instrument. Visible light gets sent to the other instrument, which is really cool because we're super efficient. So we've obtained images at 4 microns, 3.3 microns, 3 microns 2, 0.99, 0.91, and this is at the red edge of what your eye can see. So if you were looking at this disk with your eye, this is roughly what it might look like. So this is really cool. Again, these holes are I just added those myself. We did not use a chronograph or anything like that. We don't have to because the images are so sharp. The Strel ratio, are you guys familiar with that?
No.
Strel ratio just means how pointy is the star. How blobby is it? If you have bad Strel ratio, then it's a big blob, like I showed in the very beginning with seeing. If you have a high Strel ratio, then it's very sharp and pointed, and so then you can see very faint things that are located close to the star. So these are such high Strel ratios, approaching 90, 95%, 100% being the best you can do, that we don't even need a chronograph. So we just directly image, and we can see this ring very easily. Okay.
What's the spectral type of that star?
This is also an A star. It's
an A star.
Yeah,
okay.
Big, hot, massive star. Yeah. Okay, so here's the new spectrum. Here's basically we filled in this this part of the window that we needed. So this was already done. We filled in these points. Actually, we got also another 2 micron point. We didn't really need it though. And so we filled in this infrared part. And now we can really start probing the true chemical composition of this disk. So, like I said, what others typically do is they take they do a couple very complex models with a couple different types of mixtures. What we decided to do with this is take a more simple approach and also a more thorough approach. And so what we did was we basically combed the literature and found all the optical constants for all these different compositions. So you have astrosilicates, which is just basically silicates, olivine, both iron poor, normal, nominal, and iron rich, crystalline, olivine, pyroxene, carbon, organics, Titan tholins, water ice. As you can see, there's 3 different types of water ice that we had to test. Obviously these guys think theirs is correct. These guys think theirs is correct. And then you have iron and troilite, which are found in meteorites. And so in total, we actually tested more than 8,400 unique mixtures. And when I say that we kept things simple, the most complex mixture was just 2 things mixed together. Whereas, like I said before, people do mixtures of 4 or 5 things. And because this is based off of me theory, I don't know if you guys have heard about that, but basically me theory, what's that?
Scattering.
Yeah, so, and me theory assumes basically that dust grains are spheres, which is completely not true. So that leads to problems. So we, again, just try to keep things simple and be thorough. And so this is our approach. And so we were able to make a plot like this. This is all the compositions at different volumetric fractions. That means how much was in each model. Basically, 90% was a lot. There's for iron, this shows basically when looking at just the scattered light. That's the data that I obtained. If you just consider that, iron did basically pretty poorly. Red is good, blue is bad. So here, basically, what you see is that basically the silicates and some of the organics and carbon are the most favored. If you look at just the thermal emission, that's the part of the SED, where you're not resolving the disk, then you actually see the same trend. You see basically silicates and carbon are favored. And if you look at them both together at the same time, you see the same trend. Basically silicates and carbon. And if you notice here also, water ice is not really favored, especially in large quantities. You can also do a couple other iterations, changing a couple other assumptions, and you see the same trends. Silicates, organics, not much water ice. And so even though our models are not that precise, even though they're not that complex, this thorough approach basically tells us generally what is most likely in the dust that we're seeing. And generally, it's most likely that there's silicates, carbon, and not much water ice. Now, the water ice not being there, you guys shouldn't be disappointed because, remember, this is an A star. It's very hot. There's a lot of UV radiation. The dust grains we're seeing are very small. When they get chipped off of the bigger asteroids and comets, the water ice, even if it's coated in water ice, over a couple orbits, that water ice is going to be totally destroyed by the UV radiation. So there could still be a lot of water ice on the parent bodies themselves. We just may not be seeing it on the dust that we see in scattered light. If that makes sense. Any questions? Okay. So the other benefit of the high-resolution imaging that we do is we can really constrain the ring morphology. And so this is an image from Hubble of the same disk. Okay, and you can sort of see the pixels. It looks a little pixelated. That's because of the low resolution. That's because of money. Hubble had to have a small primary mirror, only 2.4, 2.5 meters. On the ground, we can have big primary mirrors, and when we have adaptive optics, we can reach a diffraction limit, so we can get very high-resolution images. So this is, again, one of our images from the ground of this disk, and you can clearly see a lot more interior to the ring and exterior, and the actual shape of the ring, how the light changes as a function of both azimuth and radial distance. And so this will allow us to really probe the dynamics of potential planets in the system. So we can fit an ellipse to this ring, we can measure its eccentricity, and that can tell us all sorts of interesting information. For instance, the center of the ring is offset from the star. Not by much, but by a little bit, by a couple AU. And that tells us that the ring has an eccentricity of around 0.05. Okay, fine. I mean, the solar system, the Kuiper belt, is not necessarily perfectly circular. The planets don't orbit in perfect circles, so that's not that crazy. And if you deproject, if you take the images that I obtained and you deproject them so that they're viewed face on, this is basically where the center of the ring is. Now we can also, because we know where the center of the ring is, we can figure out where the periastron is and where the apoastron is, which is pretty cool. So this is where the ring is closest to the star, and this is where it's furthest away. And so we see a ring-like offset disk. We think planets. Okay, where are they? What are they like? Remember this slide. Many ring-like planets or disks. Where are the planets? What are they like? So people have looked at this problem before. A lot of theoretical work has been done. Here's just some snapshots of different simulation images from different authors. Basically, all of them looking at how a planet affects the morphology of a disk. And if you look at a really a paper that to me changed the game was this paper by Eugene Chang from Berkeley, trying to model Fomalhaut's disk. Have you guys heard of Fomalhaut?
Yep.
Okay, and you've heard of Fomalhaut B and everything, right?
Yep.
So and Fomalhaut B is probably not the planet we thought it was, because it's crossing through the ring actually, and it also its spectrum its spectrum is an A star. Its spectrum looks like an A star. So what do you guys think that means?
An A star.
No.
Maybe.
No.
Foreground star.
No. So the host star. Let me help you. The host star is an A star. Any other ideas?
Reflection.
Exactly, reflection. So the best idea, the best explanation is that there's like dust basically around this thing, around this object, and it's going through the ring, which maybe makes sense. So it's collecting dust. Maybe it's just a dust pile by itself, and it's going to get smeared out over time. We don't really know. But when it first came out, it was very exciting, and Eugene Chang said, well, I'm going to constrain its mass by looking at simulations of the Fomalhaut disk, because we know what the disk looks like from the images. We can see the disk. So can we learn anything about the planet by modeling the interactions? And so here's basically a radial profile of the disk, basically of different disks for different planet masses. And so what he found was that basically, for small planets, for planets that are not that massive, you have a narrow disk, and when you make when you have a bigger planet, it causes the disk to be broader. And so he constrained the mass of Fomalhaut pretty well using this. But I was interested in using this approach to come up with a general methodology to use this on any debris disk, because I was at a conference and someone was showing a picture of a debris disk, and someone was saying, oh, so someone asked a question. So how big of a planet could be responsible for creating that disk? And the guy said, well, I don't know. We don't really have like a general tool to do that. And so I was thinking, I was in just about to head into my senior year, my last year of my PhD, and I thought I should do that. I have no idea how to do theory or any numerical simulations, but I'm going to figure out how. I'm going to get people to help me, and I'm going to do that. And so I went across the street at Arizona to the LPL, Lunar Planetary Laboratory, and I got the help of Renu Malhotra. I don't know if you guys have heard of her, but she's a spectacular theorist, and she guided me and helped me basically attack this problem. So, as I said, the person who asked this question at this conference, wanted a simple way to estimate the mass of the planet that could be responsible for creating the disk, for making the disk the way it looks. So, how can you, if you're the observer, use these models? You need a simple method. So, ideally, you want something simple, preferably an equation. The equation should take in something, you feed something to that equation, preferably disk observation, something you measure. It should then spit out something you care about, like the planet mass and its orbit. And to do this, in order for this to actually work, there has to be a relationship between planets and disks. If there's no relationship, this equation won't work. So basically, my goal was to find that relationship. And I already had a good idea that there was a relationship because of that Eugene Chang paper, that plot I just showed. And so I made hundreds of simulations on a laptop just like that, nothing fancy. And of basically a disk and a planet of varying mass and varying eccentricity, and evolved for thousands of orbits. And then I basically recorded the disk widths as a function of planet mass. As I make the planet bigger, what happens to the width of the disk? Here's what I found. Here's the actual radial profiles for dust grains of different sizes, because a disk is not just one type of dust grain, it's a whole bunch of collection of different types. And here's actually what you measure. These are these radial profiles. And so you can see already from this that as you make the planet bigger, the profile gets broader, the disk gets wider. And this is a general case now, not just Fomalhaut. So
but you're talking about single planets.
Just one planet,
when
yes.
Most systems have multiple planets.
You're probably right.
Complicated.
Exactly. So and because it's complicated, I was a grad student at the time. I said I'm going to take the simple approach first, and then we can make things a little more crazy later on. Maybe when I get a faculty job. So here's a cartoon showing exactly what happens. So here's your starting out. You have your planet, star, and your disk. As you make the planet, as you evolve, the planet, the disk gets broader over time. As you make the planet bigger, the disk gets even broader, and as you make it even bigger, it gets even broader. And you might be wondering why the planet moves further away from the disk. That's because we know that the planet should be only so close to the disk, otherwise it disrupts and destroys the disk. So I put the planet as close as I possibly could to the disk without destroying everything, and so that's why it moves its location. So if you plot up the data, this is what it looks like. These blue points are actually from Eugene Chang's paper. I got him to send me his data because I was curious, if he'd actually plotted this. He never made a plot like this, but it was in there. The data was there. So you see basically that as you increase the planet mass, the disk gets wider. Here's our general result: is these black points, and you see the same trend. Even though the slopes are different, that's okay. His was on a specific system. Ours was a general, hundreds of simulations, and we see the same general trend, which is really interesting. And you can actually spend hours fitting this line. It's super complicated to come up with an equation for a line. That's a joke, by the way. It's an equation for a line. It's very easy. So you can fit a line to this, and it's just a simple equation like this, where you just plug in the width of the disk, and you know the mass of the star, you get the mass, or the maximum mass, I should clarify, of the planet. You can't actually get the true mass, you can only constrain the maximum mass. But this is still a super powerful result that observers can now measure the widths of debris disks and constrain the maximum masses of planets using a simple equation. Even if the equation is wrong by 50%, it's still better than contacting a theorist and saying, hey, can you run like 1,000,000 simulations for me to constrain the mass of this planet? This is much faster. It's a first cut, first attempt. You can always do more intense, realistic simulations later on. So it's a very powerful result. All right, so now we can actually use this for HR 4796A. So here's, again, those theoretical radio profiles. Here's what it actually looks like for the observation. These are different wavelengths, okay? And actually, it looks broader at the longer wavelengths only because the PSF is broader at those wavelengths. You can actually correct for that, and when we do, they all basically lie on top of each other. So we can measure the width. It's about 14%, which is, for this star, about 11, 12 AU. Now we can use that width to constrain the planet mass. So here's how we do that. We'll basically plug that into the equation. We get that the planet mass must be, if there is a planet there shepherding that ring, it has to be less than about 4 times the mass of Jupiter. We can also constrain the orbit of that planet. We know that it must be further than about 50 to 60 AU away from the host star, and its eccentricity is probably similar to the disk, which is around 0.06. We can actually go further than that. So we know, remember from before, we know where the periastron and apoastron of the disk are. If we assume that the planet is aligned, apsidally aligned with the disk, such that it shares the same periastron and apoastron, they basically both have the same close approach and the same far approach, or the same locations, then we can actually estimate where the planet is most likely to be. And that's because we know that since planets orbit on ellipses, they spend most of their time near apoastron and less of their time near periastron. So when we take a random image looking for planets, there's a statistically higher chance that the planet is going to be on this side of the star rather than on this side. Even though, it's only a small eccentricity, so it's only, a 52% versus 48% chance. It's still a powerful result. And actually, we can even go further back to this image. This is the image of the ring, not deprojected. This is where that square would be, right? And this is where the planet would be. So, as you can see, this close in here is really hard for us to actually see what's going on in this image. It's really tough. It's much easier to see things further away, and so it may take several more years before, if there's a planet there, maybe it'll orbit out here and we'll see something, or the other side. It may take several more years before we see that planet, or it's not there at all. Or there's many small planets, like he pointed out. So we'll see. But we know for sure that the biggest thing that can be there is around 4 Jupiter masses. Any questions about this? Okay. The last part of the talk is a fun, interesting new system. It's called the star. The star name is HD 142527. Basically, this is a very young star, and you can see this. It has this disk right here. This is around 100 AU. You can see some spirals actually, which is really interesting. And this is again a gap, and this is now 100 AU gap. Okay, so when disks first form and planets are forming, we think that there's material there. As planets start forming and growing, they clear out material. So if there's planets there, this would be a great place to look. So this actually, there's dust and gas out here. People have found that. And actually inside the gap, even though we don't see dust, people have found gas. It turns out that there's gas streaming in towards the center, towards the star. And I'm just pointing out these spirals here. What's interesting is actually there's something going on inside here. Now you can't see it in this image, but I'll show you how you can see it. This is, I won't say it's an image. It was made using interferometry, but you can treat it like an image. Basically, there's a very likely object right here, very close, at 88 milliarcseconds, which is like 10 AU. This star is at 140 parsecs. So that's, inside 0.1 arcseconds in terms of angular scale. This is really close. And you can do that with interferometry. That's what that gives you, is the ability to see things very close in, but not that faint. You can see bright things close in, not faint things. So there's this likely object inside there. They weren't really sure what it was. It was estimated to be around 0.25 solar masses, which is a star, but still kind of interesting, because maybe the star is responsible for that huge gap. Or maybe it's not. Maybe there's a star and lots of other planets in there as well. But it's a good laboratory to investigate. And so with Magellan, again, this doesn't show up that well, but you can look there if you want. With Magellan, we can image this object, and we have visible wavelengths again. And so actually we can look in a special H-alpha filter. And maybe some of you know, H-alpha is often associated with accretion. So if you see H-alpha emission, that's a sign of accretion. And so they looked at H-alpha with MAG-AO, and we saw that this object was bright. In fact, we did something called simultaneous differential imaging. Have you guys ever heard of that? Okay, so it's when you image at two wavelengths, two filters, at the same time on the detector. And so what that allows you to do is, if you expect an object to be bright in one filter and faint in the other, and the star is the same in both, then you can subtract both images from each other, the star will go away, and all you'll be left with is the object itself. And that's exactly what happened here. So this object is very bright in H-alpha, and so that told us that basically this thing is accreting. So remember I said that there was gas all in here, falling in? This thing is accreting. So that gas is falling onto this companion, and the star itself, actually. So there's a lot of, this thing is growing, basically. That's what this is telling us. Now, what Alicia and I at DTM were interested in is there also dust around this object? Because that might really explain, that would tell us that this thing is pulling in material from the gap. That so there may have been dust in there before. Now it's falling on the inner part and the companion. And so the way to see dust really close to a star is you want to look in polarized light. And so we needed a small inner working angle, high Strel, adaptive optics, near infrared. I love MAG-AO, but we don't have the polarization capabilities to do this. And so actually what we had to use was the Gemini Planet Imager, which is a brand new advanced adaptive optics instrument and system. And some of you, in fact, on the Stardust that was handed out today, the images there from the Gemini Planet Imager. One of them is of HR 4796, the disk I was showing. Another is of, I think, Beta Pic, that planet that moved around the star. So that's putting out spectacular results. So there was this early science call. GPI just came online, and what happens often with advanced systems like this is, before a full call for proposals, where basically they invite the whole community to put in proposals, they'll have an early call where if you are awarded time, it'll be sort of like shared risk. Things may go wrong, but you may get some data, and so it's kind of like it's a gamble, but it can really pay off if you actually get the time and things work. And so there was an early science call. We applied for time. There's band 1 and band 2, typically in band 3 for Gemini. Band 1 means since it's all Q observing, they do the observing for you. Band 1 means your thing is going to get done during the semester, no matter what, unless all things break. Band 2 is second priority. So we got band 2. We're like, okay, well, we might get something. Turns out we did get it. And so here's an image of this disk, again, in polarized light. It looks just like the one you saw before. But remember, we're interested in what's going on way inside there. So the first thing we decided to do was make sure we could find that companion. And remember, it had only been imaged in this special H-alpha filter. This is actually looking at around 1 micron, and not an H-alpha, just normal imaging. So first we wanted to see if we could find that companion. And bam, there it is. This is a very nice high signal noise image. The companion is there. It's real. It was right around where we expected it to be. These dark lanes are just an artifact from the data reduction. It's how you actually produce an image, is you sort of get those features. And so there's the companion. And what we notice is actually what we often do to figure out the brightness of a recovered object is we insert an artificial source into the data and then re-reduce all the data to see what our pipeline's doing. And here's the artificial source. Here's the recovered source. And you can see it's basically extended. You know, there's some extra stuff outside of the position of the object. So that was already giving us a clue that maybe there's dust around this companion. So the next thing was we wanted to look for this dust in using the polarized light imaging. That's the whole point. That's why we applied for this time. And so normally what you do is, again, I'm just putting this up there so you can see what's done. You're basically imaging at different half wave plate angles, and you're using the Stokes parameters Q, U, Q and U to basically make a polarization map. And that's what's typically done. That's called the double difference technique, and it's very popular. It works pretty well. There's also the double ratio method, which involves a whole bunch of other math. It basically gets you the same thing, but has been shown to be a little bit better, in terms of higher signal noise detections. Now, we would like to use this, okay, because it's better. But it turns out that because you're dealing with square roots here, square roots don't like negative numbers, as you're probably all aware. And so, because we're doing PSF subtraction, we're doing high contrast imaging, we're going to have, you even saw them, negative pixels, those dark lanes. And so that's bad, so we can't really use that part. We can't use this for that. So what we did actually was we used this part first, and then we ignored that, we ignored this stuff, and then we used that part, combine the two to make a nice image. And so here's basically the steps that we performed. PCA is principal component analysis. You guys may have heard of that in other fields. It's very hot right now in astronomy, especially in imaging, because, so if you're curious, I recommend going to Wikipedia, which I love, and looking up eigenfaces. I don't know if you guys have ever heard of that, but basically the idea is you can, if you have a bunch of images of people's faces, if we had snapshots of all your faces, you could, and you didn't have a picture of my face, you could make my face using the library of your image of your faces, because all faces share similar features. And so I really encourage you to look at that on Wikipedia. And so when we go to the telescope and take images of stars using adaptive optics, we take lots of images of the star. We're interested in finding the planet. We can use all the images, just like all the faces, to make a good match and then subtract that away, leaving just the planet or the dust. And so that's what we're doing here. Here's the result. So you can see there's something there. Okay, that's great, but you can probably tell by eye that there's also some junk up here. There's some negative pixels, whatever. So it's not really not really a convincing result. But we're actually not done. We can do better. We can use something called angular differential imaging. Have you guys ever heard of that? No? Okay. Well, basically, I won't get into the details, but it's another high contrast imaging technique like PCA that allows you to improve your PSF subtraction so you can see faint things. And the data was taken such that we could do this. So after we did all this other stuff, we did another data reduction part to improve this final image. And this is what we found. So you see there's just this little blob here, nothing else really going on. So this is a firm detection of dust around this companion. And actually the fact that this dust is here tells us that previous estimates of the mass of this thing are really just only upper limits, because this dust contributes to the light that's been seen at other wavelengths. And so at most, this thing is 0.25 solar masses. It could be a low mass planet that's just enshrouded in dust, and so it's accreting. It's got all sorts of other bright things to make it bright. It doesn't necessarily need to be a very massive object. Any questions on this? Okay. So what else is another interesting feature about this dust is that it's actually offset from the companion. So these colored points right here, these orange, red, green, purple, that's the companion imaged over time at different epochs. Okay, so it's moving like this. Here's the star, so the object is moving like this, right? And this blue point is our location of the dust, and this purple one is our own you know, that first image I showed you, showing that we could detect a companion, that's where it is. And here's the polarized light showing where the dust is. So it's offset by a few AU. I don't know, maybe it's a clump of dust, you know, it's you know, sort of entrained and falling in. Maybe it's pinched. We don't really know, but it's certainly interesting. And what's also interesting is actually we see evidence for this around at least one other system. This is Lick Calcium-15. It's another young system with, you know, gas and dust. This blue thing is thought to be, you know, a young planet, and the red things are basically dust. So just showing you offset dust around two systems. So maybe this is common. I don't know. We're just starting out. Just two systems like this. There's still a ways to go. You know, we basically need to find more systems like this to figure out if this is a common occurrence or not. Okay, summary. Oh, how did that get in there? Let me put on my adaptive optics glasses. There we go. All right. So I'm using adaptive optics to resolve scattering dust grains, so we can learn about disk morphologies, and also learn about their compositions, especially with regard to the building blocks for Earth-like life. Right now, we can't image other Earths. We can't constrain their atmospheres. We're probably still 10, 20 years away from that. I was talking about that at dinner a bit. So a good proxy, a good first step, is figuring out what the dust is made of, because we can actually see that. Maybe in the future we'll be actually able to see the planets themselves. And actually, at the wavelengths that I've showed, all the images I showed, we were sensitive to planets, and we're not seeing them because they're not there, or they're fainter than they are, or they're closer into the star. So, but we can see them if they're there. We just haven't found them. And overall, exoplanets and disks is a young field. It's really, especially in the imaging side of things, we are really just getting started. Each new image and discovery literally changes the way we think. Think about HR 799 with that 7 Jupiter mass thing at 80 AU. You know, it's very strange. So each new image is awesome, and this is the future. You know, imaging is the future. Transits are great. Radial velocity is great, but imaging is really going to tell us whether there's other Earths, or whether there's other habitable Earths, because we can actually probe the atmosphere using imaging. So that's the future. Thanks a lot.
There are no other Earths. Just one. Other Earth-like planets, maybe.
Yeah, Earth analogs.
People say other solar systems, too, and there are no other solar
Nothing
systems.
accessible.
True. All right, if you have other questions, then I'm
Over there.
Where do you go next from here? Will you make more progress by using, say, the James Webb Space Telescope, or a larger Earth-based telescope, or better adaptive optics, or what's the question?
Everything is the answer to what you said. JWST actually is not going to be that huge. Well, since I'm being recorded, I should not just say that I'm not going to use JWST. It's going to be very oversubscribed. It's going to be very hard to get time on that telescope. I do have a couple project ideas for JWST for finding planets. Not necessarily. It may not be that great for the disk chemical composition stuff. Maybe different types of disks. You can actually take spectra, which will be really nice, but from the ground with better AO and with bigger telescopes like the GMT, the TMT, these are the 30-meter and giant Magellan telescopes, you're going to be able to, we're limited to seeing, like I said, 5 Jupiter mass objects. We're going to be able to start seeing, super Earth, mini Neptune, Neptune-type, Saturn-type objects, which is going to really, we're just getting closer and closer to seeing other Earths. So, hope that answered your question.
There was a very early slide where you had this device that was pyramidal with the actuators. How do I understand it being pyramidal? Is this the reverse side of it? The pyramids are not the optically functional parts. They must be the backside of the actuators or something.
The pyramid, the light passes through the pyramid to the wavefront sensor. Okay, and the wavefront sensor uses the images the pyramid makes to measure the distortion of the images, and then that tells the wavefront sensor computer then tells the mirror how to move to correct for the distortion.
So the image that upon which the correction is evaluated, or the correction to be made is evaluated. Is the same image as the one that one sees? I would think the sides of the pyramids would just mess everything up beyond all recognition.
Remember, the pyramid is just used for the wavefront sensing. So it has no. The pyramid is not involved in the. So the light that comes in is split a bunch of different times.
There's a beam splitter somewhere.
Exactly. There's a bunch of beam splitters. The first one takes light and sends it off to the AO wavefront sensor. The rest of the light gets sent to the science cameras.
If you got a beam splitter, I'm okay.
Okay, there you go. Yeah. Sorry about that.
I have a question about when you say low-resolution spectra. Essentially, you're taking the instruments and using them as essentially an image spectrometer and is pulling out the data that each image provides in terms of the brightness of the features.
Yeah, what I meant by low-resolution spectrum. Hopefully, this will clarify. Is a spectrum. You're splitting up the light, right? We can't do that because we need all the light we can get at each wavelength because these things are so faint. So all we do is we have a filter, over a very short wavelength range, at a certain, central wavelength. We make an image, we, put an aperture down, figure out the brightness of our feature at that wavelength, and we do the same thing at other filters, and then we plot that up. That's basically, if we had done that at all the different filters, at all the different wavelengths, that'd be a spectrum, or a high-resolution spectrum. But we're doing this at just a couple different filters, and so it's a low-resolution spectrum.
So it's a different bands in a sense.
Exactly.
Okay. And I have another question. In your pre-high school or pre-college years, who inspired you to be interested in astronomy?
I've loved astronomy since I was a kid. I actually just spoke to my old middle school kids about this. I was always bad at math and science, actually, as a child. In fact, I hated math. I loved astronomy, but I was almost afraid. In fact, in high school, I'd heard such horror stories about calculus that I didn't take it. And in fact, senior year of high school, I didn't want to take math at all because, I was like, this is not for me. My college counselor said, we think you should take math if you want to get into college. so I did take math, but I avoided calculus. And in fact, I was actually going to be a classics major, Greek and Latin, going into college. And I started on that path. And then I decided, I loved astronomy so much that I wanted to test the waters once and for all. So I took Intro to Calculus, and I loved it. I mean, calculus is way more interesting than any other type of math. I think calculus is beautiful. I just think it's wonderful. And then, so once I figured out I could do the math, I said I'm done with classics. I'm going to switch. And so no one really inspired me. I had books. I had my own telescope, but I never thought I could actually do it until I tried. The real math, and then the rest was history.
What are the technical challenges to be able to see Earth-sized smaller planets or Earth-sized planets, which I take it as the next sort of major goal?
So we basically need to collect more light first, and so in order to do that, you need a bigger telescope. And so even with the TMT, the 30-meter telescope, and the GMT, we are not going to be able to, we don't think, image other Earths. Another problem is that Earth is actually brightest around 10 microns if you look at its spectrum. And so, so you might say, well, let's look at 10 microns then for other Earths. Problem is, the solar system has this thing called zodiacal dust.
Yeah.
You've heard of it. And it's also very bright at 10 microns. And so, if there are other Earths and there are other systems like the solar system, they may also have zodiacal dust, and those may hide planets like Earth. And so actually that's why the LBTI, so I mentioned the LBT, but the LBTI is a large binocular telescope interferometer. My advisor, Phil Hims, is the PI of that. It's a NASA-funded mission. And what it does is it takes it's a binocular telescope, so you can take the light from the stars, and you can cancel out the light by interfering it and but detect zodiacal light around other stars. And so they're doing a survey now to look and see how likely is it that other systems have zodiacal light. Is this really a problem? And so we'll go from there.
What sort of space-based interferometers and stuff like that, which you read about sometimes, be useful, or is it just too expensive?
Sure, they'd be great. Money is a huge problem.
Yeah.
I've heard talk. Well, first of all, exoplanet imaging is becoming. I think people are starting to realize that it's going to be a very powerful technique. JWST is going to do some, but there's going to be something called, maybe you've heard of WFIRST. There's something that's in the work called WFIRST AFTA, which is basically, I think, some spy agencies donated two telescopes to NASA, and one of them, they have coronagraphs, and so we can use them for imaging. So that's going to go up into space and hopefully start finding smaller planets. But basically, what I've heard talk about now is something called ATLAST, which is designed for a 16-meter telescope, visible telescope in space, which is basically like Hubble on steroids, and that really would be a really powerful planet imager. But we won't know until we try.
Yeah, but presumably these are very expensive and it's a bleeding edge engineering.
Yes. Yeah. Definitely.
Any other questions? Well, let's thank our speaker.